This is going to be a classic hard integral video. Here we're going to look at the integral from minus infinity to infinity of cosine 3x over x squared plus 4 dx. And I found this integral and an outline for the solution on Math Stack Exchange, but I'm going to fill in all of the details. We're going to use two tools which we will derive just for completeness in order to evaluate this integral. One is that the integral from minus infinity to infinity of 1 over x squared plus 4 is equal to pi over 2. And the other is the Dirichlet integral. In other words, the integral from 0 to infinity of sine x over x dx is equal to pi over 2 as well. Okay, so let's maybe get going. So on this first tool, we're going to take this, I'll just copy it up here. We've got the integral from minus infinity to infinity of 1 over x squared plus 4 dx. Now you might say, hey, I know that looks exactly like something whose antiderivative is an inverse tangent. And you're totally right, but let's fill in some of the details just for completeness. So I'm going to factor a 4 out of the denominator. In other words, a 1/4 out of the whole thing. That's going to give me 1/4 the integral from minus infinity to infinity of 1 over x over 2 quantity squared plus 1 dx. So notice if I factor a 4 out, this is going to turn into a 1. This is going to turn into x squared over 4, but x squared over 4 is the same thing as x over 2 quantity squared. Okay, so we're off to a good start. Now let's make a u substitution. So I'm going to let u equal x over 2. So that means x equals 2u, which means dx equals 2 du. Now, furthermore, when x is tending towards minus infinity, u is as well. And when x is tending towards infinity, u is as well. So we don't need to change the bounds of integration. So let's see what that gives us. So we've got this thing down here can be replaced with u. And then my dx can be replaced with 2 du. Okay, great. So now let's see what we've got going on. We've got 1/4, and now we've got the integral from minus infinity to infinity of 2 du over u squared plus 1. Now notice this 2 and this 4 will cancel to a 1/2. And then I have the arctan of u, because that's the antiderivative of 1 over u squared plus 1. And I need to evaluate that as u approaches minus infinity and u approaches positive infinity. So these are this is an improper integral, so that means I need to take a limit here. So those limits are well known. They are pi over 2 and negative pi over 2. So this gives us 1/2 of pi over 2 minus negative pi over 2. So in other words, pi over 2 plus pi over 2. But that clearly adds up to just pi over 2. Okay, good. So we've established this first tool. Now we're going to move on to establishing our second tool, which is sometimes called the Dirichlet integral. So that's the integral from 0 to infinity of sine x dx, and we're going to show that that is equal to pi over 2. Okay, so the first thing that I'm going to do is take this integrand, sine x over x, and take a portion of it and rewrite it in a tricky way. So I'll take this 1 over x, and I'm going to rewrite that as e to the minus xy over x, where I'm evaluating that at the top at 0 and at the bottom at infinity, where these are y values. So there I've got y equals 0 in the top part, and y is approaching infinity in the bottom part. So notice if I plug in y equals 0, I get 1 in the numerator. If I let y tend towards infinity, I get 0 in the numerator. So this is all going to simplify down to this. Now next, I'll change the order of this evaluation, and I'll do that by picking up a minus sign. So I've got e to the minus xy over x, and then evaluated from infinity and 0. So I've changed that order of evaluation, but now I can easily rewrite this as negative the integral from 0 to infinity of e to the minus xy dy. So just to reiterate, I've taken this 1 over x portion of the integrand and I've rewritten it as this y integral. Okay, good. Now I want to insert that into my integral up here, which is like one of my sub goals. So I've got the integral from 0 to infinity, the integral from 0 to infinity. I'll go ahead and take that minus sign and bring it out, and then e to the minus xy sine x dy dx. So now we're going to apply Fubini's theorem and change the order of integration. So I've got a video on the channel already where we look at a case where Fubini's theorem doesn't work. So try to find that if you're interested. Okay, so let's go ahead and change that order of integration. So we've got minus the integral from 0 to infinity of e to the minus xy sine of x dx dy. Okay. So now there's a couple of ways of approaching this. We could use integration by parts, but what I want to do is rewrite the sine function as a complex exponential. So I can rewrite the sine function as 1 over 2i times e to the ix minus e to the minus ix. Okay, good. So I'll take this 1 over 2i out front. So that's going to give me 1 over 2i out front. Then I'm going to go ahead and let this minus sign distribute through and change the sign on these. So that's going to give me this integral from 0 to infinity, this integral from 0 to infinity, and then I'll let this e to the minus xy distribute onto this. So let's see what that gives us. That gives us e to the minus ix minus xy minus e to the ix minus xy. And then recall my dx integral is first and my dy integral is second. So let's see what we've got going on here. We've got this e to the minus xy distributing onto this term, and then I've just changed their order. Okay, so now maybe we'll write these with the x factored out so we can get a feel for exactly what this looks like. So notice I can factor an x out of this, or maybe I'll factor a negative x out of this, and I'm left with y plus I. And then I can factor a negative x out of this, and I'm left with y minus I. So that's important to see because it makes finding the antiderivative pretty easy. Okay, so let's go ahead and do that. So we've got 1 over 2i, then we've got the integral from 0 to infinity. And now the antiderivative of this with respect to x is going to be minus 1 over y plus I, and then e to the minus x times y plus I. So that would be the first term. And so we'll have plus, so I let that minus sign and that minus sign cancel via the integration. And then I'll have 1 over y minus I e to the minus x y minus I. And now I'm evaluating that from x equals 0 all the way up to x is approaching infinity, and then that is all within a dy integral. Okay, good. Now I want to point out that as x approaches infinity, each of these things approach 0 because the real part of the exponential is approaching negative infinity, so that whole thing's approaching 0. So all we get out is when x is 0. But when x is 0, we will get whatever is in here, but with the opposite sign. So let's maybe write that. We have 1 over 2i, the integral from 0 to infinity. And then plugging in x equals 0, we'll get 1 for this, 1 for this. But since it's the lower bound, we have to change the sign. That'll be 1 over y minus I minus 1 over y plus I, and then dy. Good. So maybe I'll go ahead and bring that up, and then we'll continue on. So on the last board, we finished at the following spot. So our Dirichlet integral was equal to 1 over 2i. And then we've got this integral from 0 to infinity of 1 over y minus I minus 1 over y plus I. So now what we'll do is combine these by finding a common denominator. So we can build up the denominator of this one by multiplying the numerator and the denominator by y plus I. just like that. And then we'll do the same thing over here. So building up the numerator and the denominator by multiplying by y minus I. Good. So let's see what that gives us. So we've got 1 over 2i, the integral from 0 to infinity. So this first term becomes y plus I over. So now notice this is going to be y squared plus 1. After we FOIL that out, notice that's essentially a difference of squares with I. And then we're going to have minus y minus I over another y squared plus 1 dy. So notice in the numerator, the y and the y will cancel, and then we'll have I minus negative I. So that's going to be 2i, which is going to cancel this 2i, leaving us with the integral from 0 to infinity of 1 over y squared plus 1 dy. Now again, that's going to be equal to the arctan of y evaluated from 0 up to infinity, and I should say here y is approaching infinity. So inverse tangent of 0 is 0. As y approaches infinity, inverse tangent is equal to pi over 2. So that's good because we've established this second tool. Now we're ready to move on to the main result. So we're going to approach this by using Feynman's trick. In other words, taking the derivative under the integral sign. So I want to point out that I worked this out not using Feynman's trick, but replacing this with a double integral and then again a triple integral, but it took pages and pages and pages. And perhaps it was not as illuminating as doing it this other way. So I've chosen to do it this other way, even though usually I skew towards putting it into a format of a multiple integral rather than doing this derivative of under the integral. Okay, so let's maybe go ahead and introduce a function. So let's set I of t equal to I'm going to write it like this, twice the integral from 0 to infinity of cosine of tx over x squared plus 4. And I want to point out that we know what I of 0 is. So notice that I of 0 is equal to pi over 2. And that's because I'll get twice the integral from 0 to infinity. Cosine of 0 is 1 over x squared plus 4, but that's going to be exactly this thing after we account for the evenness of the function. So we know I of 0, and then also notice that our goal is I evaluated at 3. And again, we can replace this doubly infinite integral with a singly infinite integral by using the evenness of the function. Cosine is an even function, and x squared over 4 is also an even function, so that's good. Now what I'll do is I'll take this derivative, so I prime, so that's the derivative with respect to t, so that's going to be equal to minus 2. We've got the integral from 0 to infinity of x times sine of tx over x squared plus 4 dx. So derivative of cosine is negative sine, but we're taking the derivative with respect to x, with respect to t, so that's why that x popped out, and then we had the minus sign because of the derivative of cosine. Okay, great. Now what we want to do is multiply the numerator and the denominator by x. So that's going to give us minus 2. We've got the integral from 0 to infinity of x squared times sine of tx over x squared plus 4 dx. And now we have an extra x in the denominator like this. So why do we want to do that? Well, we want to do that so we can cleverly add and subtract the same thing to the numerator, getting part of this to cancel with the x squared plus 4. So that's exactly what we're going to do. We're going to take this right here, and we're going to add 4 and subtract 4. So let's see what that's going to give us. So that's going to give us negative 2 times the integral from 0 to infinity of x squared plus 4 times sine of tx over x times x squared plus 4 dx. So that's what we get from the plus 4 part. And then from the minus 4 part, we'll get plus 8, the integral from 0 to infinity of sine tx over x times x squared plus 4 dx. Good. So again, that's from the -4 part where we combined it with the -2 to get a +8. So now what I want to notice is I can simplify this quite a bit. I can maybe simplify this by canceling these out. And then the next thing that I can do is make a u substitution. So maybe we'll set u equal to tx. So in other words, we have x equals u over t. So notice that means that dx is going to be 1 over t. And then the t that we introduced from this term down here will cancel the one that we introduced from the dx. And furthermore, our bounds of integration will stay the same, because when x is 0, u is 0, and when x is tending towards infinity, u is as well. So that's going to leave us with -2, this integral from 0 to infinity of sine of u over u du. Again, these t's canceled from this dx component and this x component. Great. And then we have this thing I'll just bring down. So we have 8, the integral from 0 to infinity of sine of tx over x times x squared plus 4 dx. And then from our second tool, we know that this integral is pi over 2. So that means this portion is equal to -pi. So now notice that we can see what I prime evaluated at 0 is automatically. So notice that I prime evaluated at 0, so we'll get -pi from this portion. And then sine of 0 is 0, so we have the integral of 0. So let's maybe go ahead and put that up here. I prime of 0 is equal to -pi. So I'm going to go ahead and box these two conditions that we have on our function I. Again, the -pi from here, and then that part disappears when we set t equal to 0. Okay, let's maybe go ahead and clean up the board and start back at this I prime part. So in the previous board, we ended up at the following spot. So we've got I prime equals -pi plus 8 times the integral from 0 to infinity of sine tx over x times x squared plus 4. And that's very motivating because notice we can take another derivative with respect to t and we'll be back at our original integral. So let's maybe go ahead and do that. So we've got I double prime of t. So obviously the derivative of pi is going to be 0 because that's a constant. And so we'll get 8 times the integral from 0 to infinity of cosine of tx over x squared plus 4 dx. So that's because the derivative of sine is cosine, and by the chain rule, this x pops out and cancels that one in the denominator. But notice that that is exactly equal to 4 times I of t, given our definition of I of t up here. So now what we're doing is looking for a function so that when we take its second derivative, we get 4 times the original function. So you might have seen this in a differential equations class, but we don't really need a differential equations class. We can just guess it. So that means I of t. Well, let's think about functions that stay relatively the same when you take the second derivative. Well, exponentials will do that. So notice that if we have e to the 2t, that's going to work. So its first derivative is 2e to the 2t. Its second derivative is 4e to the 2t. That's 4 what we started with. And then also e to the minus 2t will work. So the first derivative, we'll get a -2 down. The next derivative, a -2 times a -2, which is a +4 down. But we know that those will come along with some arbitrary constants C1 and C2. But now we just have to figure out what those arbitrary constants are by our initial conditions, which we argued a bit earlier. So let's also write what I prime of t is. So that's going to be 2c1 e to the 2t minus 2c2 e to the minus 2t. Now what I want to do is evaluate each of these at t equals 0 and use our conditions, which we have up there. So that's going to tell us that c1 plus c2 is equal to pi over 2. And then 2c1 minus 2c2 is going to be equal to -pi. So how can we solve this? Well, maybe we'll take this equation, multiply it by 2, and add it to the second equation. So notice that's going to give us 4c1 equals 0, which in other words, that means that c1 equals 0. But now if c1 equals 0, that tells us that c2 is equal to pi over 2. Again, that depended on our initial conditions. So up here, we can finish it all off. Notice our function, which we've represented as an integral right here, can also be represented as a linear combination of exponential functions, where c1 is equal to 0 and c2 is equal to pi over 2. So we've got that this is equal to pi over 2 e to the minus 2t. But our goal was this thing evaluated at 3. That gives us our goal integral. So let's go ahead and calculate that. I evaluated at 3 is going to be pi over 2 times e to the 6. Because we've got e to the minus 2 times 3, that's e to the minus 6. We can just bring that downstairs. So our final answer for this integral, in other words, the value of this integral, is equal to pi over 2 times e to the 6. And that's a good place to stop.